So good morning. So previously we were discussing the various normal form. So we discussed the fourth normal form and fifth normal form. So based on the multi-value dependencies and joint dependencies. So further we will discuss the various relational database design algorithms and further the dependencies. So in functional dependencies, so we will have the inference rules and minimal cover concepts. So inference rules and functional dependencies are similar to the inference rules that we make in a mathematical logic. So a functional dependency x yielding y is inferred or implied by a set of dependencies in F on a relation if x determining y holds in every legal state of database. So whenever a database state is legal, then all the functional dependencies should hold. Formally, a set of all dependencies that include F as well as all dependencies that can be inferred from F, it is called as a closure and it is denoted by the symbol F plus. So if F is a functional dependency, then all the functional dependencies which we can infer from this F, it is called as a closure and it is indicated as F plus. So this plus is written as a superscript. So here you can see the example of a functional dependency. So SSN yielding employee name, birth date, address and department number. And department number is determining the department name and manager SSN. From this particular functional dependencies, so we can make an observation that SSN is determining the department number. Further, this department number is determining the department name and the manager SSN. So, with this, what we can conclude is this SSN is determining the department name and the manage department a manager SSN. So this can we can determine. So further we can also determine that SSN is determining SSN itself. So that is the self dependency and department number it is determining the department name. So because we can take only one part of out of it. So that is the department name. So all other things we can establish. So department number is determining the department MGRSSN. So like that. And here also SSN determining employee name, SSN determining birth date, SSN determining address. So all those things we can infer. So whatever we infer, the entire set complete, it is called as a closure. So closure of a functional dependency is all the set of functional dependencies that can be inferred from F. So closure of F plus of F is a set of all functional dependencies that can be inferred from F. To determine a systematic way to infer dependencies, we must first set the inference rules. So these inference rules are similar to the mathematical inference rules. So given a set of functional dependencies, we can infer additional functional dependencies that however hold in the F. So the few proposed methods of these functional dependencies include Armstrong's inference rules. So Armstrong is a person, mathematician, who has given the inference rules. So there are three inference rules according to this Armstrong. So one is reflexive rule, augmentation rule, and transitive rule. So these rules are used to infer the additional functional dependencies. So one set of functional dependencies is given over here. In order to infer additional things, we need these kind of inference rules. So here, the first rule, that is reflexive. So if it has to be mathematically represented, then if um, if x is uh, like this, if x is containing y, then we can infer x is determining y. So this is the first reflexive rule. So the reflexive one rule states that the set of attributes always determines itself or any of its subsets, which is obvious. So if x contains y, then x determines y. So which means the self-determination. So SSN determining SSN itself or any other subset that is there on the right side. So that functional dependency, it is based on the reflexive rule. The second rule is the augmentation rule. So the augmentation rule says if x is determining y and then xz determines yz. So here xz indicates it is a union of the set of attributes x and z. So if there is a functional dependency which is holding, then if we add attributes at both the sides, so still the functional dependency will hold. So if this is the functional dependency, if I add certain set of attributes on both the sides, then still the functional dependency should hold. So this inference rule, it is called as augmentation. So that is the second rule. So the third Armstrong's rule, inference rule. So these are also called as Armstrong's axioms. Okay. So the transitive rule. So in the transitive rule, if x is determining y and y is determining z, so then we can infer the x is determining z. So just like the transitive mathematical logic relationship. So these three are called as Armstrong's inference rules. So first one is when x is a, y is a subset of x, then x determines y, then x determining y, then if you add both the attributes to both the sides, then still the functional dependency holds. So it is called as augmentation and then transitive. Some additional inference rules are also there. So they are decomposition, union, and pseudo transitivity. So before this, so we may also provide a proof to these three rules. So suppose if y is a subset of x, Then let us consider the two tuples. Um, so here the condition is, so x is containing y. So which means y is a subset of x. So and there will be two tuples t1 and t2 exist in some relational instances such that uh, t1 of x is equal to t2 of x. Then we can say that t1 of y is equal to t2 of y because x is containing the attribute y. So then we can say this x is determining y. So this is only possible when x contains y. So here this contains the, let us assume x is the SSN comma name and y is the name. So here SSN comma name and y is name. Then if two tuples are there where SSN and name are same, then we can infer that here also they will be same. For this to hold, the only condition is, so y must be a subset of x. So the second rule is, so the additional inference rules include the decomposition. So in decomposition, so we have, so if there are more than one set of attributes on the right side, so we can divide it. So x determining yz will become x determining y and x determining z. So this rule is also called as the projection rule, or it is called as projective rule. Here this second one, that is union. So if x is determining y and x is determining z, so left side of both are same, then we can combine the right side. So this rule is also called as additive rule. Then pseudo transitivity, if x is determining y and wy is determining z, then we can write wx is determining z. So which means, so y is determining z and y is being determined by x. So which means the place of y can be replaced with x. So this rule is called as pseudo transitivity rule. So the proof for these rules can be inferred like this. So here, so this is the given one, that is x determining yz. So which means we can write, so the proof that we must provide is x determines y and x determines z. So here we can write yz determines y because according to the first rule, um, this part is the subset of the right side. So we can write an inference like this. So yz determining y. We can also write yz determining z also, because this is a subset over here. This contains this side. So when we have this particular rule, okay, so x determining yz determining y, then by applying the transitive rule, we can write x determining y. So similarly, we can prove this one also. So x determining yz and yz determining z. So we can write x determining z. So based on the uh, reflexive rules and the transitive rule, we can deduce x determines y and x determines z. Then the fifth one, that is a union or additive rule. So x is determining y and x is determining z. So if this is the case, then by applying the augmentation, we can write x is determining xy, and then xy is determining yz, and then we can write x is determining yz. Then the last one, pseudo transitive. So x is determining y, wy is determining z, then wx is determining wy, and w can be wy, it is determining the z, so we can write wx is determining z. So this is all by applying the two rules that we saw in the beginning, that is the augmentation rule and reflexive rule. So augmentation rule means, so if x is determining y, so then we can add an attribute to both the sides, right? So this rule being applied in both. So if x is determining y, then and wy is determining z. So what we can do is, so we can add an attributes. Okay. For the first rule, that is x determining y, we have, for this both the sides we can add w. Okay. So then it becomes wx determining wy, but wy is determining z. So as given over here, so we can easily write wx is determining z. So just by adding the attributes to both the sides, so we can deduce these things. But if by any chance if we have two same sets, so then we can write only one part. So if it is xx, then we can write x. So they apply the rules of reflexive and augmentation. So in order to prove these three rules. So the inference rules, the first three are called as sound and complete. So sound, because given a set of functional dependencies f on a relational schema, any dependency that we can infer in f can be deduced using these three rules, and every relational state must satisfy these dependencies. So that's why these rules are called as they are sound, and they are complete because using the inference rule 1, that is the reflexive, till augmentation and transitive repeatedly to infer the functional dependencies until no more dependencies can be inferred in a complete set of all possible dependencies, and thus by determining the closure. So since the closure and all set of functional dependencies can be found using only these three rules, so these three rules are said to be sound and complete. So closure of x under f. So for each set of attributes x, we determine the set x plus of attributes that are functionally determined by x. So that is based on the functional dependency f. So then x plus is called the closure of x under f. So this is for calculating the closure of an attribute. So far in the beginning we discussed the closure of a functional dependency. So we can similarly find the closure of a attribute. So closure of a attribute indicates all the other set of attributes determined by this particular attribute. Okay. So there is a algorithm for determining the closure, so which we will discuss in next class. So you can put your attendance.